Hello, welcome to MIT. I'm sure you guys have had a chance to check out campus. Maybe you've seen some of these memes around. It's the thing this week to put these Megamind memes. In fact, this morning, I was thinking about what is the history of these Megamind memes? Where did they come from? So I decided to watch a video. And while watching the video, there was this like AC noise in the background. Oh, it was super annoying. And I thought to myself, like, how can we get rid of this like annoying AC noise? Well, turns out this is actually a really big problem for sound engineers and software engineers around the world. And in fact, that's what the problem we're going to try and fix today. So today, we're going to try and get rid of the problem, get rid of this echo from this signal we're going to hear right now. Okay. We're going to remove this echo. So, what do we know about sound and signals? So if we take this sound signal, the amplitude, well, first of all, we need to know a few key characteristics about the sound signal. We have the amplitude. The amplitude is how high you can go, how loud you can get, and how soft you can get. The frequency is going to be how many cycles can we achieve within a single second. So in here, we can think of it in terms of low pitch and high pitch. So the low pitch here means that we only had one cycle in this 1 second. But over here with the high pitch, we had maybe like 5 or 6 of these cycles within a second, right? So low frequency, high frequency. So the idea is we can actually think about signals in terms of multiple ways, right? So we can think of it in terms of its time domain. So basically, x-axis is going to be the seconds, or it's going to be the samples. And then the y-axis is going to be the amplitude, how loud you can get, like we mentioned. But the thing is, we can also think about it in terms of our frequency domain. So remember, the frequency is the low pitch, high pitch. So we can think of it in terms of our frequency domain. And in fact, these are actually equivalent signals. Make sense? So this is pretty much just which frequencies appear in this sound signal. Cool. Right, so we listen to our echo, so maybe we'll listen to it one more time. Right. Very echoey. It's hard to tell what's going on. So this is a plot of what we just heard. So the original sound is actually this point right here. At sample 0, we hear the original sound. It flies from Denver to San Francisco. But then a little bit later, we have this sort of kind of depressed version. It's not quite the same audio level as before, and it's a little bit delayed, right? So this is going to be our echo, and we want to get rid of this. Right? So this is kind of the time domain representation of what we just heard. So how can we think to get rid of this kind of unwanted part of our signal? Well, a lot of sound engineers what they usually do in practice is come up with this artificial, kind of this, they construct a new signal called a filter to get rid of this. And the one intuitively that we can think of to get rid of this is to construct a filter that just simply inverts this. Right? So think about it like if we were to combine this signal with a signal that was to have just an inverted stick at this point, we would kind of get rid of this, right? So intuitively, this is what we would do. And this is what this looks like, right? We want to combine this and that to be able to get rid of this. Cool. The only problem is when we go to do this, it actually doesn't really work, which kind of sucks. So this is what happens when we combine this signal, this filter, H of n, with our original signal, X of n.
Flights from Denver to San Francisco.
Okay, so what happened there? It sounds a little better. It almost sounds like the delay, or the echo got delayed a little bit. Yeah, that's exactly what happened actually. And this plot is a good representation of what happened. So this is the combined signal. We combined our filter and the previous signal we saw in the previous slide. So we actually achieved our goal. We actually ended up canceling out and this echo at this point. But as sort of like a side effect, an unwanted side effect, what ended up happening was we ended up introducing this other like echo that came maybe a little bit after. It was a little more delayed, and it was a little less loud. Right. So we can think about, so now we can kind of scratch our heads and we go, okay, so well, how do we get rid of this one? Well, the thing is we can add another stick here. We can construct another filter where it has this stick at this N0 point, N0 point, and then we can construct another stick at this point here to try and get rid of this. But the problem is that now we're just going to kick the can down the road again. And so basically the stick is going to continue to shift to the right. And we can do this infinitely, as we can see in this plot here. So it's a little bit futile, actually, to think about how we can continually kick the can down the road, but never actually like completely remove it, right? So this is a really big problem. But what can we do to kind of completely avoid this altogether? Well, we can think about the signal in terms of its frequency domain. Way back when we started the talk, we talked about a signal's frequency. We can think about that to try and get rid of this. So how can we do that? So here's a little snapshot of what we were doing before. So this is to show how inefficient it is to do what we were doing before, which is just combining the signals together in its time domain. It's almost like we have to, so this red is the filter. It's almost like we have to multiply at every single point, every single microsecond of our audio. And there's a lot of microseconds in our audio. I mean, that's what makes it entirely inefficient to do it in this method. However, if what we did instead is we thought of it in terms of its frequency domain, we can completely bypass the really, really complex, inefficient, and otherwise expensive combination which we were doing before in its time domain. Because, and this is the kicker, because this combination is equal to multiplication, simple multiplication in the frequency domain. So the basic idea is we're just shifting how we look at our signal to be able to do what we want to do a little bit better. Why? Because it's actually super cheap to be able to go from this time domain to the frequency domain. And it's cheap to do the multiplication. And so what we can do is simply go to this side of this equation, do the multiplication, then go back. And we've completely avoided this really hard to do operation that we were doing before with the triangle in the previous slide. And so a little more in depth. So this is kind of an example. So let's just pretend that this is our signal in the frequency domain. This is our filter in the frequency domain. The idea is, we can think of it, we can simplify the problem to, this is what we want to keep in our original, the flights from Denver to San Francisco, like, this is the original sound we want to keep. This is the echo we want to get rid of. So what we're going to do is we're going to construct this sort of array to multiply by here, right? So the idea is, if we want to just keep 3, we're going to have a 1, because 3 times 1 is 3, right? So same idea here, we're going to make everything else 0 here, because we don't want anything other than the 3, right? So we're going to say 0 times 0 is 0, clearly, but then here's the point. 1, our echo, times 0 is 0. We've just eliminated our echo using the frequency domain. And here's yet another view of what's going on. This is just the same plot as what we showed in the beginning of the talk. So this is our signal in the frequency domain, hertz cycles per second. So the idea is, if a portion of this signal is causing the problem, the echo that we're trying to get rid of, we can simply introduce, ta-da, this filter that just blocks off part of that like annoying signal. And this is what allows us to completely get rid of it. And what we end up hearing afterwards is this.
Flights from Denver to San Francisco.
Oh, beautiful. We've successfully gotten rid of this nasty echo that we were trying to get rid of. And here's a plot of what happened. Not that one. So here's a plot of what was happening. We have our original signal here, and we have no more echo here. So now I can turn on the other video, the one that was happy. And so the idea is now, just to recap, what we've done is we've thought about our signal in just a little bit of a different way. We've used a different characteristic of our signal to completely bypass a really expensive operation. And now I guess we can go back to finding out about these Megamind memes that we've been seeing around campus. So thank you.